Okay, in this video, we're doing Calc D Note 7, page 3. We're still doing like double integrals. All right, so there are a couple different ways that the bounds are going to be given to you, especially if you're dealing with rectangles. So the first one will look very familiar. It's just, your standard inequalities. So x can go from 0 to 1, y can go from 0 to 3. That's actually probably not the most common way, but maybe it is. I don't know. So that's one way you can be presented with it. You could also be presented with just the picture that represents that. So this is a region in the xy plane. You'll also see this. This one's a little confusing the first time you see it. So it's -2 less than or equal to x comma y less than or equal to 3. So this is equivalent to saying x is between -2 and 3 and y is between -2 and 3. It's more efficient to just kind of combine it, but the first time you see it, that's pretty weird. Another way you'll see it, which I think is probably the most common, is a region R will just be described to you. So here, you're being told 3 to 5 by -2 to 6. So anytime you see that, the first part is going to be x's, the second part's going to be y's, and if there's a third part, it will be z's. So this is equivalent to 3 to 5 for x and -2 to 6 for y, using those inequalities. Now I think it's useful to look at the bounds and try to draw the region in the xy plane. So I'm going to do that also. So looking at the first one, we would end up with this rectangle. So x goes from 0 to 1, y goes from 0 to 3, and then you kind of shade it in. That's the region in the xy plane. And then remember, the integrand is a surface that's either above or below this region, and you're trying to kind of find volume is the easiest way to think about it. So that would be our region for the first one. For the second one, it's going to look like this. So x is -2 to 3, y is also -2 to 3. So again, you're just getting a square in that case. That's the only thing. It has to be a square. It's the only way you could describe it using that particular notation. And then for the third one, I mean, I know everyone can draw regions in the xy plane, but I do think it's useful to keep this in mind as you're doing things, that these bounds do represent a region in the xy plane. And you do have to pay attention when you're given the integral. You have to pay attention to like the order of integration. Are you doing dx dy or dy dx? Because you have to match up the bounds. All right, now what I'm going to do is I'm going to do an integral in two different ways. So we want to evaluate the double integral over the region, and then our integrand is y sine of xy, and then dA, which means we get to pick the order that we want to integrate. And then r is x goes from 1 to 2, and y goes from 0 to pi. So I'm going to start out, I'm going to do the like kind of default option that everyone seems to go with. Everyone always seems to want to go with dy dx. So I'm going to set up my integral, make sure I match up the bounds. I'm color coding, so you can definitely see that I did that. Now the issue is I need to try to integrate y times sine of xy, where y is the variable. That's like y times sine of 3y or something like that. That's an integration by parts problem. And so I'm going to do it using the table method because the derivatives of y go to 0 when you take them with respect to y. So I'm going to set up u, v, and then the sine. I do this a little differently than a lot of people, in particular my v column is just v. So I don't start with dv and then go on diagonals. I just start with v and go straight across. So u is going to be y. And then v, I have to integrate sine of xy, where y is the variable. So the integral of sine is negative cosine. But since I have x times y, y is the variable. So the derivative there would just be x. So I need a 1 over x. So I'm going to get negative 1 over x and then cosine of xy. So that's maybe the trickiest part. Well, no, definitely not. That could be the trickiest part of this integral. You'll see there's something trickier in this case. The derivative of y is 1. And now I need to integrate again where y is the variable. So there's a bunch of x's hanging around, but all the x's are constants, so we don't need to worry about those. So the integral of cosine is going to, the integral of cosine should be sine, and I've written this wrong. The integral, but then I did it right, so that's weird. The integral of cosine should be sine, but there should be an x, so another 1 over x. So I'm going to get negative 1 over x squared, and then this should say sine of xy. So hold on, I'm going to try to change that. This is always a nerve-wracking thing. So this is why I write them out ahead of time. Here we go, sine, bad handwriting, sine. There we go. Okay, so we're at this point. And now what I want to do is I'm going to do uv and then the sign, and then uv. Like, you just keep going. So this will be, we still have our outer integral. U times v is negative y cosine of xy over x, and then minus negative, which will become plus, and then sine of xy over x squared. So fortunately I did it right. I don't know how that's happening. I guess because I kind of knew the answer while I was doing it. So don't forget the bounds for y, and then there's still the dx. So I'm going to substitute for y now because I should, right? And one thing that will happen is that when I plug in 0, so when I plug in pi, so the integral still exists. I'm going to get negative pi cosine of pi x over x. And I'm going to get plus sine of pi x over x squared. The key thing is, when I substitute 0 for y, in the first part, I get 0 times whatever, so that's gone. And then when I substitute into the sine, I get sine of 0, but the sine of 0 is 0, so that's also gone. So 0 actually zeroes out the whole thing. So this is all we're left with, so I'm going to put in the dx. Now this is crazy, because if you're just looking at it, you might have no idea how to integrate it. I do think if we get a common denominator, though, it starts to look a little more obvious what's happening. Maybe I'm going to write it in a very strange way because I know what it should look like. So I'm going to write negative x pi cosine of pi x, and then minus sine of pi x times negative 1. So that was a weird thing that I did. But then I'm going to say over x squared. So what I think is happening here is that we're actually dealing with the quotient rule. And my tip off that it's the quotient rule is that the denominator is squared. You do not run into this all that often, so this isn't like a giant important idea. But sometimes when you're asked to integrate something that looks a little weird, if the denominator is squared, it may be the case that you're actually dealing with the quotient rule, and you're just going to try to reverse that. So I think if this is the quotient rule, it would be bottom derivative of the top. So it looks like the bottom function is negative x, and then that's the derivative of the top, so it would be minus top derivative of the bottom. So the top function, I think, is sine of pi x. So I think we're really trying to integrate from 1 to 2 the derivative of sine of pi x over negative x. But then we're trying to integrate that with respect to x. We're integrating the derivative. That should just take us back to the original thing. So I think we're just going to get sine of pi. I know this is actually happening. We get sine of pi x over negative x from 1 to 2. When you plug in 2, you get sine of 2 pi, which is 0. And then when you plug in 1, you get the sine of pi, which is 0. So all of this work is to get 0. But that's the value. So this, I don't know, maybe wasn't the best order of operations. Maybe we should have gone dx and then dy. And I'm trying to make the point that most people, when they set this up, will always go dy dx. It's like our default brain mode is to go dy and then dx, because I think we just are used to doing integrals with respect to x. Sometimes it's going to be easier to go dx dy. So let's try that same problem. We're going to go dx dy on this one. So immediately I need to integrate y times sine of xy dx. So I would just do this in my head because I've done a lot of these. I'm going to try to show the work. I sometimes think showing the work is harder. So I'm going to let u equal xy because that's the thing inside of sine. And now you got to keep in mind which of the differentials comes first, right? So du is definitely something. Since it's dx, I want to take the derivative of this thing with respect to x. So I'm going to get the derivative of x is 1. And the derivative of y is a constant, so it just hangs around, it's constant multiple. So I just get y dx. So that's because I'm really finding like du dx here. So I get du is y dx, which means that 1 over y du is equal to dx. And then I'm actually going to show the substitution here because I think it is kind of valuable. So our original integrand is y sine of xy dx. We sub for everything. So the y is still there. We get sine of u, and then 1 over y du. The y and the 1 over y just cancel, so this becomes the integral of sine of u du. And the integral of sine of u du is negative cosine of u, like plus c, but we know we're actually doing a definite integral, so we don't really care. So I'm going to go back to my original now and just sub this in. So I am doing the integral from 0 to pi. We found that that whole thing, when we integrate with respect to x, gives us negative cosine of xy, and then x is going from 1 to 2, and then there's still a dy. So that's what you do. Sometimes you can do u-substitutions. I actually think that if you get good at doing them in your head, it's almost less confusing to just do it in your head than it is to write down all the work. But if you want to write down the work, no problem. I'm going to plug in 2. Nothing exciting happens here. I'm just doing the fundamental theorem. Negative cosine of 2y, and then minus negative, so plus cosine of y dy. Now I need to integrate. Remember to reverse the chain rule. So I'm going to get negative 1/2, because there should have been a 2, sine of 2y, and then plus sine of y from 0 to pi. So I'm writing y equals there. There's no reason for that. I could have just done 0 to pi, except like 9 out of 10 times I do y first. So I'm just like, in my mind, it's built in, right? Y equals and y equals. Now here we run into the same scenario. When I plug in 2, I get the sine of 2 pi, which is 0, plus the sine of pi, which is 0, minus when I plug in 0, the sine of 0 is 0. So this thing overall is just giving me 0. But there you go. Okay, so that's where I'm going to stop this one. I will be back in the next video where we're going to talk about, I guess, page 4 of these notes, because why would we not? All right, so I hope this was helpful, and I will see you in the next one.